Okay, good evening everyone. I am Shivani Dhok and I welcome you all for the summary session of the course of Digital Signal Processing and its application. So this is the last session that I will be taking, and so what I'll be doing is I will be taking up few questions which were there in your assignments in last 12 weeks. These are selected questions, and yeah, these are due to restricted time. I won't be able to cover all the questions that were covered. So I have chosen few questions which are interesting and are have been asked as queries in the portal. Okay, so there is no recap this time. So we will directly jump to the question answers today. Okay, so let's start. So here is the first question, and this question is question number 5 from week 1. Okay, so this is an interesting question which looks at the Fourier transform or continuous time Fourier transform of a periodic signal. Okay, so let's quickly go and see what exactly has been asked in this question. So it says that which of the following is true about the Fourier transform of G prime t. And what is G prime t? G prime t is the periodically repeated version of time limited function gt with period t naught. So how does it look? So what we will do, without loss of generality, what we will do is we'll take g of t, something like this. May not be symmetric, but tm by 2 to tm by 2 minus tm by 2 to tm by 2, and this something like this. So what it says is this is the band of our interest, that is T naught, and our signal is band limited or time limited in this region T naught. So this is an assumption that we will do. G of t belongs to, or rather G of t is non-zero for t in a range of minus tm by 2 to tm by 2, where this tm is a value which is less than t naught. Okay, this is an assumption. You can do away with this assumption and still land to the same results that we are going to get today. Our aim is not to focus on these assumptions, but to look at a time limited signal or time limited function and its periodic form, and how the Fourier transform of the periodic form relates to the Fourier transform of the original signal, that is g of t. Now what they say, this is, let's start g of t. Now they are saying that we have another signal g prime of t, which is basically the periodically repeated version of this function gt with a period t naught. Okay, so how does this look? So this g prime of t is periodically repeated function gt with period t naught, which means that it is located at every integer multiple of t naught. And since it is located at every integer multiple of t naught, this k ranges from minus infinity to infinity. So what does this mean? This means that g of t is located at every integer multiple of t naught. Okay, so this is how my g prime of t look. Now if we go to our options, there is something called as g of f, where this g of f is basically the Fourier transform of g of t. So this gt has a Fourier transform g of f. And how does this g of f look? So basically this is continuous time Fourier transform of this continuous time signal. It looks something like this. It is by definition minus infinity to infinity g of t into e power minus j 2 pi f t dt. Okay, but now we considered that this g of t is a function that is non-zero only from minus tm by 2 to tm by 2. So this is equivalent to integral minus tm by 2 to tm by 2 g of t into e power minus j 2 pi ft dt. I'll number this as equation number 1. Okay, so now we have a control over the Fourier transform of this signal, that is g of t. But we are not interested in Fourier transform of this g of t. We are interested in the Fourier transform of this g prime of t, which is periodically shifted version or periodic repetition of this signal g of t. So let's again look at this g prime of t. So this g prime of t, which is summation k running from minus infinity to infinity, g of t minus k times t naught. This is a periodic function with period t naught. Okay, and let g prime of f be the continuous time Fourier transform continuous time Fourier transform, or what we say CTFT of g prime of t. Now we have seen this earlier. For a periodic signal, let me use a different color here. Yeah, for a periodic signal, let's say g prime of t, the CTFT depends on the continuous time Fourier series and it is given by how does it look? We have seen this earlier. G prime of f is 2 pi summation k running from minus infinity to infinity ak into delta f minus 2 pi f naught t. Sorry, 2 pi f naught k. And what is this f naught? This f naught is 2 pi by, sorry, f naught is 1 over t naught, and yeah, okay, so there won't be a 2 pi here, sorry. Yeah, it's like this, and where this f naught is 1 over t naught, which is the fundamental frequency. Okay, so now let us find AKs. AKs are CTFS, or continuous time Fourier series coefficients. And these are given by 1 over t naught, integral over a period of t naught, g prime of t into e power minus j 2 pi f naught t k dt. Okay. Now I'll choose this period from minus t naught by 2 to t naught by 2. You can choose any one, but since it is convenient, I'll choose it from minus t naught by 2 to t naught by 2 g prime of t. And what is this g prime of t in minus t naught by 2 to t naught by 2? So that is basically when you have k equal to 0. In that case, my g prime of t will be exactly equal to my g of t. So in that region, or in this regime, this g prime of t is equal to g of t into e power minus j 2 pi f. I'll write it like this, k f naught t dt. Okay, now if you go back and look at this equation of g of f, how does this look? Okay, let me reduce this further. Now this g of t is not equal to 0 only for t in a range of minus tm by 2 to tm by 2. So I can write this equation, or I can write this ak as 1 over t naught integral minus tm by 2 to tm by 2 g of t into e power minus j 2 pi kf naught t dt. Now what you have to do is you compare this equation with this equation. Okay, so let me again write down this g of f on the next page. So what I have a of ak as like this, and from equation 1 we have g of f as integral minus tm by 2 to tm by 2 g of t into e power minus j 2 pi f t dt. And when we compare this and this, what we observe is ak's. So this ak is 1 over t naught, this function g of k. When I put f equal to k times f naught, I get g of g. I get ak scaled by a factor of 1 by t naught. So what I get, ak is equal to 1 over t naught g times g of k times f naught. So this is my ak. Now we'll substitute it back to the equation where we find the Fourier transform of g prime of t, which is g prime of f. Therefore, g prime of f is given by 1 over t naught, we write it properly, summation k running from minus infinity to infinity, 1 over t naught g k times f naught into delta f minus f naught, k times f naught. I made a mistake, I think, here. Yeah, simply k times f naught. Yeah, like this. Okay, so this is what we get. So this is what we are getting here. So now if you go and check the options that we had, so here the options were like it depends on t naught, it depends on delta Dirac function, it depends on periodically repeated function of g of f, sampled version of g of f. So basically it's just asking us to figure out what all parameters it depends on and in what fashion. So we'll just go back to this equation and we'll see. So the first thing that is very evident is it depends on t naught. So this depends on T naught, not only through this but from F naught as well. Okay. Another thing that is evident by just observation is this thing, that it includes or it has something that depends on direct delta function. Okay. So includes direct delta function. And the last thing that we need to figure out is this thing. So what is this? This is basically sampled version of g of f sampled with period naught. Okay, is it clear? Any questions? So what all things it depends on? It depends on T naught, it depends on Dirac delta function, and it depends on the sampled version of G of f. Okay, so what all things we saw? Yeah. So it depends on T naught. It depends on T naught. It includes Dirac delta function, and it is the sampled version of G of f in the frequency domain. Okay, is it clear? Any questions? So this is the answer that we have. This was a multiple answer correct question, and this is what we get. Any questions at this point? Okay, if there are no questions, then let me move on to the next question. So this is a question from week 1, and this is question number 7 from week 1. This I thought is an important thing to take because it just revises the system properties in a better way. So it says that if a shift invariant system satisfies this property that y of n is equal to y1 of n plus y2 of n for all xn equal to x1 of n, x2 of n, then the system is linear and shift invariant. So let us first see what is given to us. First thing given to us is the system is shift invariant. Second thing given to us is this x1 of n. If I give as an input to that system, it results in an output of y1 of n. And if I give input as x2 of n, it gives output as y2 of n. And when I give an input as x of n, which is x1 of n plus x2 of n, it results in an output y of n, which is equal to y1 of n plus y2 of n. So what does this mean? This means that the system is additive. Okay, this is given to us. But what do we mean by linear and shift invariant system? For an LSI system, that is linear and shift invariant, it has to be shift invariant and it has to be linear. And this linearity we can break into two parts. The first part is additivity, and the second part is homogeneity. Okay, now whatever data is given to us, in that we know that it is shift invariant and we know that it is additive, but there is no knowledge of homogeneity given to us. This thing we don't know. No information regarding homogeneity. Now the thing is, we know that additivity is being satisfied and we know that it is a shift invariant system. So can we produce a counter example where the system is shift invariant, it is additive, but it is not homogeneous? So let us try to cook up that example. Okay. So what we will look at now is a counter example. where the system is shift invariant, it is and additive, but not homogeneous. So one such example is I have a system y of n, system output y of n, which is x conjugate of n. So if I give an input x of n to this system, then it will give me y of n, which is x conjugate of n. So now if I give, so if I give input c times x of n, my output will be c times x of n conjugate, which is c conjugate into x conjugate of n, which is not equal to c times x conjugate of n, which is equal to c times y of n. So basically what is happening here is this conjugate is also changing the constant that we are multiplying with. So here we are getting conjugate of the constant which we are multiplying, but at the same time this system is linear, it is shift invariant, but it is not homogeneous, which means that based on the given information, it might happen that the system is not linear and shift invariant, even if it is additive and it is shift invariant. Okay, so which means that this system is not homogeneous, which means it is not an LSI, that is linear and shift invariant system. Okay, so the correct option here is false. Any questions here? Okay, any questions at this part? If there are no questions, then let me move on to the next question. Okay, so this is a question from week 1 and it is question number 8 from week 1. This was asked by someone in the portal probably last year, but so I kept it as it is. So it says that adding more and more aliased versions of a signal onto itself causes, and this is a multiple option correct question. So the first option is constructive interference at t equal to integer multiples of sampling time, destructive interference at t not equal to the integer multiple of sampling time, constructive interference at t not equal to the integer multiple of sampling time, and destructive interference at t equal to the integer multiple of sampling time. So here this ts is the sampling duration or sampling time, and we have seen in either week 2 or week 3. So as discussed in the lectures, and it was given as a challenge to show mathematically if this holds. I'm not going to go into details of that. As discussed in lectures, Then we add more and more aliased versions of signal onto itself. It causes one, constructive interference, at every integer multiple of sampling duration. That means that the first option is correct. And destructive interference at T naught equal to n times Ts, which means the second option is also correct. Any questions? Okay. If there are no further questions, then let me move on to the next question. So next question here says that find the DTFT, that is discrete time Fourier transform, of the sequence x of n equal to 1 for n ranging from -3 to 3 and it is 0 otherwise. So what is given? It is given that we have a signal x of n and this is equal to 1 if n is from -3, -2, -1, 0, 1, 2 and 3 and it is equal to 0 otherwise. So this is the given signal. Signal or sequence are the same thing. And what we need to do? We need to find DTFT of x of n. So let's say this DTFT is given by capital X of little omega. Okay, so let me quickly recap you what exactly is the DTFT. The discrete time Fourier transform or what we call the DTFT of a signal x of n is given by x of omega equal to summation n running from -infinity to infinity x of n into e power minus j omega n. Okay, so now let us use this definition to find the DTFT of our given x of n. So therefore, this x of omega is equal to summation n running from -infinity to infinity. But if we look at our x of n, It is equal to 1 only from n equal to minus 3 to 3, and it is 0 otherwise. Okay, so now if we substitute it back in this equation here, what we get? So this x of n is equal to 1 for n running from minus 3 to 3, and it is 0 otherwise, so remaining summation terms go to 0 into e power minus j omega n. Okay, so what do we get? We get summation n running from minus 3 to 3 e power minus j omega. Now we have seen this kind of summation multiple times in this course, but since it is a revision class, I'll write it properly here as well. So this particular thing here, this is a finite, this summation is a finite geometric progression with first term as e power j3 omega, common ratio is e power minus j omega, and number of terms is 7. Okay, so therefore x of omega I can write as first term, let me name it A, R and N. So this is equal to A into 1 minus R power N divided by 1 minus R. So what do we get? Here A is e power j3 omega, 1 minus common ratio is e power minus j omega, and n is 7. So this will be e power minus j7 omega whole divided by 1 minus e power minus j omega. So now we'll use our standard trick that we have been using. So we will take e power minus j7 omega by 2 common from here, and from the denominator e power minus j omega by 2 common. Okay, so what do we get? So now this e power j3 omega remains as it is. Then we have e power minus j7 omega by 2. Inside the bracket we will have e power j7 omega by 2 minus e power minus j7 omega by 2 whole divided by, from the denominator we have taken, rather we are taking out, so from the denominator we are taking out common e power minus j omega by 2. So inside the bracket we have e power minus j omega by 2, sorry, plus j omega by 2 minus e power minus j omega by 2. Okay, so now let us just focus on this part, these constant terms which are outside. So how does these look? So we have e power j omega common, then we have a 3 from here, then we have a minus 7 by 2 from here, and then we have a 1 by 2 from here. So what do we get? So this is equal to e power j omega 3 minus 6 by 2, which comes out to be equal to e power j 0, which is 1. Okay, so these constant terms are 1. So what are we left with now? So therefore x of omega is equal to e power j 7 omega by 2 minus e power minus j 7 omega by 2 whole divided by e power j omega by 2 minus e power minus j omega by 2. Now I'll divide numerator and denominator by 2j. These are standard tricks that we use in signals and systems or digital signal processing. Okay, and now we will use the property that sine theta can be written as e power j theta minus e power minus j theta divided by 2j. So for the numerator, theta comes out to be equal to 7 omega by 2, and for the denominator, theta comes out to be equal to omega by 2. So using this, we have x of omega equal to x of omega equal to sine of 7 omega by 2 divided by sine of omega by 2. And be careful, this is valid if e power minus j omega is not equal to 1, which implies that in the unit range of omega, which is from minus pi to pi, omega is not equal to 0. So this is one case. Now since we don't know what is going to happen for omega equal to 0, let us try to solve it. Okay. So now if omega equal to 0, this x of 0 becomes summation n running from minus 3 to 3. 1 remains as it is, e power minus j 0 times n, which is simply summation n running from minus 3 to 3, 1. And this, when we simplify, comes out to be equal to 7. Okay, so the final answer that we get is x of omega is equal to sine of 7 omega by 2 divided by sine of omega by 2, and this is for omega not equal to 0, and it is equal to 7 for omega equal to 0. Is this clear? Any questions? Any questions in this part? Okay. If there are no questions, then let me move on to the next question. Okay. So this question was a part of week 4, and it is question 3 of week 4. This is very interesting question. I really like this question. So what it says is, it's actually giving away a trick to solve this question. So what it says is, determine the value of this integral using Parseval's theorem. So before even starting this question, what I'll do is, I'll first note down what exactly is the Parseval's theorem. Okay. So this is a continuous signal, continuous in its independent domain or time domain, let's say. So let Parseval's theorem. So suppose I have a continuous time signal which is x of t, and it has its continuous time Fourier transform with angular frequency capital X of omega, sorry, x of omega, then integral minus infinity to infinity magnitude of x of t square dt is equal to 1 over 2 pi integral minus infinity to infinity magnitude of x of omega square d omega. So this is the Parseval's theorem, and what they are asking us to do is they want us to use this Parseval's theorem to figure out the integral value given here. Okay, so now this looks a little bit clumsy because of the arguments that it has. So what we'll do, we'll try to simplify it a bit. Okay, so what is given to us is, I'll write it as I, which is integral minus infinity to infinity sinc square kx minus c dx. And what is this sinc function? So the sinc function, let's say sinc of y, is defined as sine of y divided by y. So it looks something like this. Okay, so now what we will do, we'll try to simplify this little bit in the to get it in our desired form, or to simplify it a little bit. So what we will do, we'll substitute. I just want to get rid of this linear argument. I just want one variable here. So I'll substitute kx minus c as t, which means that I have x as t plus c by k, which means dx is dt by k. And since my t is varying from minus infinity to infinity, since my x is varying from minus infinity to infinity, my t will also vary from minus infinity to infinity. So therefore, I becomes integral minus infinity to infinity sinc square t dt by k. Okay, so this k I'll keep as it is, 1 over k integral minus infinity to infinity sinc t whole square dt. This is one and the same thing. Another thing, this sinc function is a real function. So if I take square or if I take magnitude square, it is one of the same thing. So this I can also write as 1 over k integral minus infinity to infinity magnitude of sinc t square dt. So this is like 1 over k integral minus infinity to infinity magnitude of x of t square dt, where x of t is exactly equal to your sinc function. Okay, is it clear till this point? Any questions? Okay, if this till this point, if it is clear, then you compare this equation here and this equation here. So these are exactly the same expressions. Okay, this integral, if you compare it with this integral here, it is exactly the same. So now using Parseval's theorem, what I can do, I can replace this by this part. Okay, this using Parseval's theorem. Okay, so using Parseval's theorem, now my integral that I am trying to solve, that becomes I equal to, we have a factor of 1 over 2 pi outside. So this is 1 over 2 pi This k is getting carried forward from here. Integral minus infinity to infinity magnitude of x of omega square d omega. Now, why did I do this? Why can't I simply integrate in time domain instead of going back or going into frequency domain? A simple logic to do that is, here we have a sinc function, and it is a well known fact and something that you should remember, that this particular this particular sinc function, if we have, has a frequency domain representation as a rectangular function. So you need to note that if I have a sinc in time domain, then this gives me a rectangular function in frequency domain. And similarly, if I have, okay, I'll write this, if I have a rectangular function in time domain, by duality of continuous time Fourier transform, it gives me a sinc in frequency domain. Okay, so this is known to us, this is a known fact, and this you should keep in mind because this will be coming up frequently in whatever things you will study in your future courses. Okay, so this is an important thing to know. So now suppose I don't know what exactly the relation or what constants and what all things it depend on. So what I'll do is I'll try to give you a relation between the sinc and this frequency domain representation, and we'll start from a very generalized form. Okay, so now what, instead of going from time domain to frequency domain, I know my sinc is in time domain here and I need to figure out my frequency domain equivalent. What I'll do, I'll start with a very generalized form in the frequency domain and take inverse DFT, inverse DTFT to get sinc in the time domain, and then we'll map it to the sinc that we have here to get the actual Fourier transform that we have. So what we will do, consider y of omega given by this function here. So we have minus b by 2, b by 2, and a rectangular function with amplitude a, and this is my y of omega and this is my omega axis. And now what I need to get, I need to get inverse CTFT to get my y of t. So how can I get that? Y of t, this is a very generalized form, let me write it down, generalized form. Okay, so this y of t is obtained by 1 over 2 pi integral minus infinity to infinity y of omega into e power j omega t d omega. Okay, so now what we have, this y of omega is non-zero only from minus b by 2 to b by 2. So this integral limits now become minus b by 2 to b by 2, and in this range this y of omega takes the value as capital A. So A into e power j omega t d omega. Okay, so therefore y of t is 1 over 2 pi. This A is also constant, I can take it outside, it doesn't depend on values of omega. Then we have minus b by 2 to b by 2 e power j omega t d omega. So this I can write as a over 2 pi e power j omega t divided by j t from minus b by 2 to b by 2. So what do we get now? So this is equal to a over 2 pi e power j bt by 2 minus e power minus j bt by 2 upon jt. So what I'll do now, I'll rearrange this a little bit. Okay. So I'll rearrange this as a over pi t into e power j bt by 2 minus e power minus j bt by 2 upon 2j. And now I'll again use the same formula that we have, or same identity that we have used for sine theta. So sine theta is equal to e power j theta minus e power minus j theta by 2j. So I'll use the same logic here, but here my theta is bt by 2. So therefore this gives me a upon pi t into sine of bt by 2. Now I want to write this as a sinc function. Okay, so now if I compare, I have this part. Okay, this part. So here I have a t outside, but I'm lacking b by 2. So what I'll do, I'll multiply and divide the numerator, and I'll multiply numerator and denominator by b by 2. So I can write this as a by pi into b by 2 multiplied by sine of bt by 2 divided by bt by 2. And this term here is basically equal to sinc of bt by 2. Okay, so what do we get now? Finally, we get ab over 2 pi into sinc of bt by 2. So if I summarize this, summarizing, if I have ab over 2 pi sinc of bt by 2 in time domain, then its CTFT is given by this function here with an magnitude as a and ranging from minus b by 2 to b by 2. This is omega axis and this is x of omega. Okay, so this relation we have built, and this is how it will look. Okay, so if you are able to memorize this, well and good. If you are not able to memorize this, just start from here, from the very basic form, and go back to the sinc function, and then your life will be easy. Okay, so now given to us is what? Given to us is x of t equal to sinc t. So now if I compare this and this, what do I get? It means that my b by 2 equal to 1, which means b equal to 1. And in similar way, ab by 2 pi is also equal to 1, but my b is equal to 1, so therefore a equal to 2 pi by b, which comes out to be equal to 2 pi. Okay, so now if I, okay, yeah, so this is what we are getting. Just a minute. Sorry, b is not equal to, b is 2 and 2, so this comes out to be equal to pi. Okay, so therefore this thing here has CTFT. This is not x, this is y. This has a CTFT as I have omega here, then here I have x of omega, and that x of omega now has an amplitude of pi, and it starts from b by 2, where b is 2, so it starts from minus 1 to 1. Okay, so now what we have? So therefore we have x of omega is equal to pi for -1 less than or equal to omega less than or equal to 1, and it is equal to 0 otherwise. Now let us go back to the equation that we were trying to solve, or the integral that we were trying to solve. So we were trying to solve this particular thing, that is I equal to, just copy paste it there. Yeah, this integral I equal to 1 over 2 pi k integral minus infinity to infinity x of omega, magnitude of x of omega square d omega, and this is exactly equal to integral minus infinity to infinity sinc square kx minus c dx. Okay. Okay, so now let us substitute the x of omega that we have got. What is x of omega? X of omega is equal to pi, but in a range of -1 to 1. So therefore we get 1 over 2 pi k integral, it is non-zero only only between -1 to 1. X of omega is pi, its square d omega. Now this pi is a constant, pi square is a constant, I can take it out or take it outside the integral. So I have pi square by 2 pi k integral -1 to 1 d omega. So 1 pi gets cancelled, and then we have pi by 2k, and this integral from -1 to 1 d omega is simply difference between the upper and lower limit, which comes out to be equal to 2. So this 2 and this 2 also gets cancelled. So what we are left with is pi by k. Now suppose you knew that the sinc function or this particular relation, if you knew, you could have, you don't have to solve this question in time domain. You can easily move to the frequency domain, and it's only this much. Only this much you need to solve. That's all. So this is how simple it is when we move and use the properties of Fourier transform. So finally what we have got, so therefore integral minus infinity to infinity sinc square kx minus c dx comes out to be equal to pi over k. Okay, any questions? Is it clear? Okay. Okay, if it is clear, then let me move on to the next question. This is from week 5, question number 12. Okay, so it says that which of the following is true if Z transform of x and y have region of convergences as Rx and Ry respectively. So what is given to us is this x of n has a Z transform as capital X of Z with region of convergence as Rx, and this y of n has a Z transform as y of capital Y of Z with region of convergence as Ry. Okay. Yeah. Okay. So now what we need to do is they have given us two different cases. One is the linearity property and one is the convolution property. And then they have asked us to comment on the region of convergences of these two cases. Okay. So now we'll resort to the properties of Z transform that we have been looking at in week 5. So what it says is the first property is linearity property. So it says that if I know the Z transform of x and y, then the Z transform of AXN plus b times y of n has a z transform as a times x of z plus b times y of z, and with region of convergence as at least Rx, that is region of convergence of x, intersection with Ry. So why is this intersection is clear, but why is this at least coming up? This at least is coming up because due to linearly adding up these terms, there is a possibility of pole zero cancellation. Okay. In similar way, okay, so let us first look at linearity. So it says that ROC of AX plus BY is at least Rx intersection Ry. So this is what we have got. So this is the correct answer. Yeah. And another one is the convolution property. So it says that if I know the Z transform of X and Y, and if I convolve them, there is X of n convolved with Y of n. And if I take its Z transform, then that will be equal to X of Z multiplied by Y of Z. And region of convergence will be again at least Rx intersection Ry. And this is again for the same reason. That is, when we are multiplying, there might be some sort of pole zero cancellation. So the ROC might improve or increase. The ROC region might increase. Okay. So for convolution also, the same ROC will come up. That is at least Rx intersection Ry. So these are the correct answers. Is it clear? Okay. If not, then let me move on to the next question. Okay. So this question is from week 8 and it is question 1 of week 8. This is related to the Butterworth filter design. So it says that which of the following is not true for the poles of H analog of S of a Butterworth filter. So now they are asking us what properties does this analog filter that is designed using Butterworth approach, the properties that are not followed by this particular transfer function or system function. Okay, so there are 4 options. The first option is the poles occur on a circle of radius omega c. The non-real poles appear as complex conjugate pairs. The third option is the non-real poles are as mirror image about the imaginary axis. And the fourth option is the poles are at an angle of pi by 6 to each other for n equal to 3, where n is the order of the filter. Okay, so here what happens is, so it is a Butterworth filter. So for a Butterworth filter, of order n and cutoff frequency omega c, the poles or the kth pole is given by omega c, sk is equal to omega c into e power j 2k plus 1 plus n over 2n pi. Okay. So now magnitude of Sk is equal to omega c, which means that for all k, Sk's lie on a circle of radius omega c. Okay. So the first option here is correct. Now the second option says that the non-real poles appear as complex conjugate pairs. So for second option, this Butterworth filter is a real filter, real valued filter in time domain. And for a real valued filter, the poles are always in the complex conjugate pairs. Okay, so the second option is also correct. The third option says that the non-real poles are as mirror image about the imaginary axis. So here is our imaginary axis, j omega axis, this is sigma axis, and they are saying that if I have a pole here, then I have a pole here also. Now what will happen if I have a pole that is located in this region? This we have seen, this is correct. But if I have a pole here and it is a causal system, so I'll have a region of convergence something like this. Then in that situation, this pole which is in the right hand plane will make the system unstable. So yeah, sorry, yeah, 1 second. Sorry, ROC won't be like this. ROC doesn't include poles. So my region of convergence will be something like this. So now here this pole which is in the right half plane will make the system non-causal and unstable. So therefore, this option is wrong. The we rather discard those poles which are in the right hand side plane. So they can't be mirror image. They can be mirror image only with respect to the real axis and not the imaginary axis. So this is wrong. And the last option is the poles are at an angle of pi by 6 to each other for n equal to 3. So now let us try to see that. So when n equal to 3, Sk is omega c into e power j 2k plus 1 plus n is 3 divided by 2n, that is 6 pi. So this is equal to omega c into e power j 2k plus 4 by 6 pi, which is equal to omega c e power j k plus 2 pi by 6. Now we'll just see the consecutive poles. That is, we'll see the difference in angle for k equal to 0 and k equal to 1. But for that, let us see what is this angle of Sk. So this angle of Sk is basically this part. So this is given by k, this is 3, sorry, k plus 2 by 3 pi. Okay. So now what we will see, we'll check angle of S1 minus angle of S0. So this is equal to, for k equal to 1, this becomes 1 plus 2 by 3 into pi, minus for k equal to 0, this becomes 2 pi by 3. So this is equal to pi minus 2 pi by 3, which comes out to be equal to pi by 3, which is not equal to pi by 6, which means that the last option also is wrong. But wait, what was asked? We were asked to figure out which of the following is not true. So basically, what we have is this statement is true, this statement is also true, this statement is false, and this statement is also false, which means the correct options that we have to mark is this one and this one. In your exam, don't make mistake that I just made. Be careful what exactly is asked. Otherwise, you will mark exactly the complementary options which you don't have to mark. Okay, is it clear? Any questions? Any questions at this point? Okay, if there are no questions, then let me move on to the next question. This question is from week 10 and it is question number 6 from the 10th week. So it says that the time domain differentiator has a DTFT as h of omega equal to j omega from minus pi to pi, and now we need to find the time domain representation of this particular thing. So what we need to find is inverse DTFT to get h of n, and we need to figure that out. So inverse DTFT for any signal is given by h of n equal to 1 over 2 pi integral minus pi to pi j omega into e power j omega n d omega. Okay, so now this j is a constant, I can take it outside. So I have j over 2 pi integral minus pi to pi omega into e power j omega n d omega. This is like integral uv, so this is first term, this is second term that we will take. So what we get is j over 2 pi, we have omega into integral e power j omega n from minus pi to pi. Then we have integral minus pi to pi e power j omega n over j n d omega. So this is equal to j over 2 pi. We have omega into e power j omega n upon j n from minus pi to pi minus e power j omega n upon j n square from minus pi to pi. So now if I simplify this, this becomes j upon 2 pi into e power j pi n plus pi into e power minus j pi n over j n minus I have e power j pi n minus e power minus j pi n whole divided by j n square. Okay, now e power j pi n and e power minus j pi n is nothing but minus 1 to the power n. So now if I substitute it back in this equation, I get h of n. Achha, another thing to note here is when we got this particular equation, we are inherently assuming that both of these cases that n is not equal to 0, here also n is not equal to 0. So this h of n, whatever we are finding is for a case where n is not equal to 0. We'll take the case where n is equal to 0 separately. Okay, so this now becomes j over 2 pi integral pi into minus 1 to the power n plus pi into minus 1 to the power n upon jn minus minus 1 to the power n minus 1 to the power n upon jn square. So this goes to 0. So what we are left with, this j cancels with this j and this pi gets cancelled with this pi. So we have 2 times minus 1 to the power n upon 2n, which is equal to minus 1 to the power n upon n for n not equal to 0. Okay, now we have the impulse response for n not equal to 0. The next thing that we need to figure out is the value of h of n for n equal to 0 to completely define this particular thing. Okay, so now for n equal to 0, we have h of n as 1 over 2 pi integral minus pi to pi j omega into e power j omega n d omega. So therefore h of 0 equals to 1 over 2 pi integral minus pi to pi j omega into e power j omega 0 d omega, which is equal to j over 2 pi. This e power j omega 0 is 1, so integral minus pi to pi omega. So now this omega, this is an odd function, which means this integral will be equal to 0. Okay, so what do we get? Therefore, this h of n is equal to minus 1 to the power n upon n for n not equal to 0, and it is equal to 0 for n equal to 0. Is it clear? Any questions? Any questions till this point? Okay. If there are no questions, then let me move on to the next question. So this question says that which of the following statements are true? First one, all causal systems are rational. Second one, all rational systems are causal. Third one, all causal and rational systems can be written as summation m equal to 0 to capital M bmz to the power minus m divided by 1 minus summation n equal to 1 to n a n z to the power minus n. So this last one is correct that we have seen in the class. Now what is left is to figure out whether the statements that are given here, that is all causal systems are rational and all rational systems are causal, if those are correct or not. Now if we want to prove something, we need to prove it for all the cases. But if we want to disprove something, one counter example is sufficient. So now what we will do, we'll try to construct some counter examples for both of these cases. Okay, so now let us first look at the first option. So first thing that we'll do, First thing that we will do is we'll try to figure out counter examples for option 1. Okay. What is a causal system? A causal system is some system which depends on, or whose output depends on, the current or the past values of output. It shouldn't depend on the future values of input. So the current output depends on the current and past values of input and not on the future values of input. Okay, so now consider the following systems. I'll change, make this on next page. Yeah, okay. So consider the following systems. The first one is y of n equal to magnitude of x of n. Then second option or second example is y of n equal to log of magnitude of x of n. And third is y of n is equal to e power x of n. Now you observe these three input-output relations that I have just written down. So what you can see is all of these systems depend only on the current value of input. So the outputs, or for that matter, let's do this also. Yeah, the outputs of the above systems, just to make it more nice, I'll do this. The outputs of the above systems depend only on the current and the past values of the output of the input, which means that the systems given in option A, B, and C are causal. Okay, but these systems transfer function cannot be written in rational form. So this means that all causal systems cannot be represented as rational systems or are not rational. Okay. So the first option that is given to us is wrong. Now let us figure out the rational. Just figure out So if we can get some counter example for the option 2. So we'll do same thing now. Let me add a page. So this is counter example for option 2. Okay, so what does it say here? So now we have to build a counter example for option 2, and the option 2 was all rational systems are causal. So now we need to try and consider a rational transfer function which is non-causal. So now let us consider this transfer function. So consider h of z, which is some transfer function of some system, as z, let's say minus z plus 1 plus 2z to the power minus 2, minus 1, let's say. Okay. Okay, fine. So we have this thing now. So we have this thing. Now if I take the inverse Z transform of this, how can I take? I need to get a sequence h of n, and I can get this by comparing it with h of z as summation n running from minus infinity to infinity, h of n into z to the power minus n. So now if I compare it one by one, so this 1 here corresponds to the case when my n equal to 0. So my h of 0 is equal to 1. So this is my h of 0. Now if I have n as 1, so I will get a coefficient as h of 1. So here I have 2 as my h of 1. And similarly, here z has a power of 1, which means that if I have n as minus 1, I'll get it here. So I have minus 1 here as h of minus n. Okay, so this h of n is a sequence which is minus 1, 1, 1 is located at n equal to 0 and 2. So how does this sequence look? I'll just write it down again. This h of n is minus 1, 1 and 2, and 1 is located at n equal to 0. This looks something like this. Let me draw it. Okay, so this is n, and I'm plotting h of n. So I have minus 1, minus 2, 0, 1, 2, and so on. At n equal to minus 1, it is minus 1. Write it. Yeah, at n equal to 0, it is equal to 1. And at n equal to 1, it is equal to 2. Okay. So now we have seen this property in our lectures, that if for a causal system the impulse response should be 0 for all negative values of n. But here we have h of minus 1 as non-zero. Here h of minus 1 is equal to minus 1, which is not equal to 0, which means there exists a value of n which is less than 0, for which h of n, that is the impulse response, is not equal to 0. Okay, but for a causal system, add a page, but for a causal system, h of n is equal to 0 for all n that is negative, which means that this system is non-causal. But it was rational. So therefore, there are systems which are rational but non-causal, which implies that all rational systems may not be causal. Okay. So this means that the second option that is given to us is also wrong. All rational systems may not be causal. We just saw a counter example. Is it clear at this point? Any questions? Any other questions that you want me to solve in this course? So this is all that I wanted to cover today. So this brings us to the end of this course and end of the sessions that I will be covering for you people. And just before ending, I'll just summarize what all things we have done in this course. So we started with with the concept of sampling. Then we looked at the Z transform concept. Then we looked at the DTFT or the frequency domain representation concept. Sorry, first we looked at the frequency domain representation concept. Then we saw that only that much representation is not that useful for us. So we wanted some tapering down of the signal so that we are able to analyze all the possible signals in the frequency domain. So for that we looked at the Z transform. Once we looked at the Z transform, we looked at the rational systems, and then we went on to go and look at design of digital filters. For designing digital filters, we looked at two different aspects. First one was the infinite impulse response filters, and second one was the finite impulse response filters. For infinite impulse response filters, what we saw that we took inspiration from the known concepts of analog filter design, for example, Butterworth filters, Chebyshev filters, and then used transformations from analog domain or S domain to Z domain. And the most famous transform that we looked at or was the bilinear transform, for which allowed us to use a transfer function that was there in the in the S domain to Z domain without changing the stability, causality, and the nature of the filter. And for designing the IIR filter, we looked at two approaches. One was Chebyshev filter and Butterworth filter. After that, we looked at the finite impulse response filter. And for finite impulse response filter, what we did, we wanted some ideal filter design in our mind. We wanted that particular frequency response. However, that frequency response has the time domain representation as a sinc function, and sinc function is an infinite response filter. Now, in order to make it finite response, we truncated it. We truncated it to get a finite impulse response filter, and that truncation led to Gibbs phenomena kind of thing, and therefore to avoid that kind of issues, we use smoothing functions which are known as window functions. And after that, so we looked at different window functions like Hanning window, Hamming window, and other rectangular window, triangular window, etc. After we did the filter design concepts, after that we went on to discuss the concepts which are related to how to realize these filters, whatever we have designed. And we said that for realizing any filter, only three components are sufficient. One is an adder block, another is a delay block, unit delay block, and another is a constant multiplier or a gain multiplier block. And for doing the realization of the system, we looked at two fundamental representations. The first one was direct form 1. The second one was the direct form 2 representation. And after that, we looked at another important representation, which is lattice structure, which helps us in reducing the implementation complexity. After that, we looked at um, the cascade and the parallel cascade representation. So what they say, if we have small blocks of filters already available to us, or system blocks already available to us, and there is another system function which is simply a multiplication of the transfer functions of the available blocks, or addition of the transfer function, or combination of it. So instead of realizing it from scratch, we can either connect those small blocks in parallel or connect those small blocks in series to get our desired transfer function. So this was done using the um, cascade and parallel representation. And after that, in the last week, we looked at another important concept of discrete Fourier transform. Discrete Fourier transform is nothing but the sampled version of uh, discrete time Fourier transform. So what we say, we want to do processing in the frequency domain using our computers, but since the omega, little omega, is of infinite precision, it is continuous in nature, we can't do it. So we will sample it in the frequency domain to get a discrete Fourier transform DFT. And that DFT can be used to compute or to perform convolution operations and other stuff. And and another important concept when we saw was circular convolution and the relation between the circular convolution and the discrete Fourier transform. There are other many concepts which are related to discrete Fourier transform. For example, we didn't look into the properties of DFT in detail, and we also didn't look at the faster implementation of discrete Fourier transform, which is known as the fast Fourier transform. So you're most welcome to look at those concepts in your textbooks. I will highly recommend to look at the fast Fourier transform representation or implementation of the discrete Fourier transform. It is an important concept, and many times questions show up related to that in GATE exam and other places. Okay, so that's all from my side today. If you have any other questions or doubts, feel free to ask. Thank you for attending today's session and all the best for your exams. If you have any queries, then the meeting is open for 1 or 2 minutes more. Feel free to ask. And if you don't have any questions, you are free to leave the meeting.
Ma'am, will there be another session for review?
No, this is the last session from my end. I don't know if there is another session from the other TA which is taking sessions in parallel with me. And in case you have any, sorry?
Yes, ma'am. What were you saying?
Yeah, so this session will be uploaded on the YouTube and you will get the notes for this session. If you have any questions regarding or queries, you just post in the Q&A portal. I'll try to reply back there.
Okay, ma'am. Actually, yesterday I posted some doubts, which is
Okay.
not taken up in the revision session. That's why I
Yeah.
asked.
Yeah, because I had told to post it out till 14th of night. I was not in a position to look at the portal yesterday due to my other commitments. So I have no idea what was posted yesterday. So because of that, but I'll open up your doubts and reply back to through mail to you. That I can do.
Okay.
Yeah.
Okay.
When is your exam? I'll
Then
reply back before that.
okay, ma'am. Okay. Thank you, ma'am.
Yeah. Yeah.